Hello, this is day 3 of the daily push-up challenge, and you look man, at day 3 I can feel my biceps growing already. But with Alberto's permission, I've modified the challenge such that I'll be doing an incline push-up instead of a floor one, so that it won't stress my body, because I really don't do a push-up a lot. But anyway, our problem today looks fun. But before that, incline push-up basically looks like this. You incline your body, and then 1, 2, 3, 4, 5. Okay, so no pressure at all. Like, instead of being on the floor, you incline yourself like that. But anyway, our problem today reads, sum the series m squared n over 3m multiplied by n 3 to the n plus m 3 to the n, where both m and n runs from 1 to infinity. Okay, so right at the start we can simplify the series. So I'm thinking, dividing the whole series by the factor m squared over n. Okay, so that the numerator, okay, becomes 1, and then the denominator, so we divide by m squared over n. Let's leave 1m outside the parenthesis, and then mn let's put inside the parenthesis. So that could give you 3m over m multiplied by, so the n will cancel here, 3m over m, plus in here the m will cancel, so you have 3n over n. Okay, and so we can let I don't know, an equals 3n over n, so that s will now become sum of m, sum of n equals, so this will become 1 over am multiplied by am plus an. Okay, and of course, since m and n are like dummy variables, I can of course always write this in such a way that the subscripts, the m and n, are swapped. Okay, their places are swapped. So where were we? I believe we did 5, 6, 7, 8, 9, 10. Okay, so after swapping that, what do we do? So I can add this sum together. Okay, so I can do 2s equals summation of n am plus an plus an plus am. Okay, and of course that simplifies to an, so they have a common factor, times an times am plus an. So the first term will have in the numerator an, it doesn't matter, because the am plus, in the end when you add them, they now have the same denominator. The numerator becomes an plus am. It will cancel with a common denominator, an plus am. So the final result will just be 1 over an. Okay, which of course is just the sum of n. If we write it in terms of the original definition, in terms of the 3, okay, this will give you m over 3m multiplied by n over 3n. Okay, so look, all m terms, they are now factorized. All m terms are multiplying each n terms, and vice versa. Okay, so in other words, I can write this as a single series, okay, which only concerns with that single factor, which has the form n over 3 over n, and then you just square it, right? Because they are each, in this new thing that we wrote here, each term is also multiplying all of the other terms when you expand the multiplication. Okay, so we can write it like that. So let's call this something like, I don't know, t. Okay, so let's continue with the push-up. 11, 12, 13, 14, 15. Man, even with the inclined push-up, it still hurts on my elbow. But anyway, what do we do here? So I'm thinking, let this be t squared. So we won't be dealing with a squared summation, okay? And let's do this. Let's multiply it by 3, okay? Such that the summation will now become, so note that this summation starts from 1, right? N equals 1 to infinity, so that gives you n over 3 to the n minus 1, okay? And then let's shift the summation. Let's make it such that n will start by 0. So that translates to making n, instead of n, making it equal to n n plus 1, right? So this becomes summation of n from 0 to infinity. So the numerator now becomes n plus 1, and then the denominator now becomes 3n. Okay, so why are we doing this? We're doing this because look, if I subtract from this equation now 3t, if I subtract from that the original t, which is what we had here, the square root of this one, summation of n over 3 to the n. Okay, this obviously will give us 2t. Okay, but that will just be equal to, so note that 3t, the first term here, begins at n equals 0. Okay, so let's get the 0th term of the summation, because our t begins at n equals 1. So the 0th term is, if n equals 0, the first term is just 1, correct? Because that is 0 plus 1 over 3 to the 0, which is of course 1, right? And then the rest of the term, instead of beginning at n equals 0, will now begin at n equals 1. So sum n equals 1 to infinity of n plus 1 over 3 to the n. Okay, so now you see here why we're doing this subtraction, because recall that our t itself is just of the form summation n, which begins at n equals 1 to infinity n over 3 to the n. Okay, so now you have a very simple summation that looks like 1 plus the sum of n equals 1 to infinity, and then the n will cancel, so you only have 1 over 3n. Now this is a simple summation to deal with, because if you recall, this is just a arithmetic, no, not arithmetic, geometric series. Okay, so where were we? Damn, I forgot. I believe we're at 15, 16, 17, 18, 19, 20. Okay, so how do we sum this? This is just equal to, this geometric series is just equal to the first term, which is 1/3, over 1 minus the constant factor that you multiply your geometric series with. In this case, is also 1/3. So that gives you 1/3 over 2/3, which is just, of course, equal to 1/2. Okay, therefore, all in all, 2t will be equal to 1 plus 1/2, so that is 3/2. Okay, of course, obviously, that means t equals 3/4. Okay, so now going back to the equation, we know that 2s, s is of course the sum that we're interested in. 2s is equal to t squared. That means s is equal to 1/2 t squared, which is equal to 1/2 3 over 4 squared, which is just equal to, so what's 3/4 squared? That's 9 over 16 times 2 is 9 over 32. Okay, so I believe we're at 20, 21, 22, 23, 24, 25. And just in case I lack like 25, and also I want to, you know, compete with Mark Andaya, he's also at the hundreds. Let's make it 30. 26, 27, 28, 29, 30. Okay, now they're even bigger than the start of the video. But anyway, yeah, it's 9 over 32. How do you know that I'm correct? So actually, I cheated initially. I actually fed this exact summation. I asked Mathematica to evaluate it, and let me check. Yeah, lo and behold, its answer is 9 over 32. So I'm gonna like paste it somewhere below my video, the evaluation of Mathematica, just to, you know, validate myself, just to see if that we're not kidding with our final answer. But in this case, the sum of this particular series, which came from, I didn't mention this, Putnam, a problem from Putnam 1999, is 9 over 32. Thank you very much, guys, and see you next time. Bye-bye.